All right, everybody, 2 o'clock, welcome in. Sorry I'm a little bit late today coming in. There's a class in front of me that was a little bit over. So, welcome back to this isn't dynamics, this is statics. Welcome back to statics. A couple of announcements. Homework number 1 was graded just as a reiteration from, so make sure to check that and that your grade is the same as what you responded to by email. Homework number 2 has also been posted. I posted it last night. That's going to be due next Thursday. That'll be on 2D and 3D particle equilibrium. So we'll start some three-dimensional stuff today. Exam number 2 is going to be next Friday, which is December 18th. I'm planning a review session probably for Thursday night, and also have some amount of review during class next Thursday. So look forward to that. A lot of people mentioning in that first homework and some of those bonus questions that they appreciate the exam reviews. So I'm going to do my best to squeeze in a little bit of review here and there for you guys, just so you sort of know what to expect for the test. All right. With that said, I did post a new set of lecture notes as well on 3D vectors. So we'll dive in on that today. So let us do that. All right, let me get rid of this guy and we'll pull this guy back up. Here we go. Okay, so new topic today, and that is 3D vectors. So we're kind of in the mode now of going from 0 to hero. 2D vectors tends to be pretty easy. And then once we get to 3D vectors and three-dimensional behavior, people kind of start to come off the rails. So make sure that you're coming to lecture and kind of tight on all this 3D stuff as we move forward. All right. So topic, 3D vectors. So we'll just discuss 3D vectors first, and then we'll talk about 3D particle equilibrium as we sort of move through this set of notes. All right. So we know that if we have some vector in space, we can resolve it into components. We did this with 2 dimensions, and we can do the same thing for 3 dimensions. So we'll start there and talk about resolution of forces into 3 dimensions. So last few lectures, we sort of focused on 2-dimensional components. 2D vectors and equilibrium. Okay, now we move to 3D. Okay, and just like how we resolved vectors in 2 dimensions into typical Cartesian coordinates, we can do the same in 3D. And so similar to 2D vectors, which are like vectors in the x, y plane, we can resolve vectors in 3D to sort of these like x, y, and z directions. Okay, so let's take a look at maybe some example or an example of doing this. All right, so let's say that we have some random vector out in space. And now I'm going to do this in 3D. So I'll make a coordinate system here that's like an XYZ coordinate system. Here's your typical X, Y, and then we're going to give ourselves a third dimension here. It's a little bit difficult, I know, to sort of draw in 3D, on a 2D page, but we sort of do our best here with imagining that Z is coming out at us. Rawr. Okay. So here we got X, Y, Z, and let's consider that we have some vector in space here that's some vector F. All right. So it's kind of out in space, and maybe we give some dimensionality to this by sort of projecting this vector into the XZ plane and sort of seeing what that might look like. So we'll say that this vector F is sort of like in this particular plane here. Okay. Okay, so contained in this plane. Right. And let's say that this particular vector f makes an angle with the y-axis, which we're going to call here theta y. So this guy makes an angle with the y direction, which here is this angle theta y. All right. So just like we do in 2D, we could take, what is this force F, which is in like this 2D plane here. So you see we have kind of like this two-dimensional plane. We could resolve this force F into like a y direction and a direction that's sort of like in the xz plane. So what do I mean by that? Well, I can resolve this into what is like this Fy, and also some force that's in just like this little bit of the plane here. And I'll call this Fh, just some arbitrary vector Fh. Okay. Now, after I've sort of like done this, I can understand then that the vector F is going to be some combination of whatever I resolved in the y direction plus whatever I resolved in f direction. So here this is like Fy plus Fh, right? This is just similar to what we did in like 2 dimensions, Fy plus Fh. Where here we can say something like Fy is equal to the magnitude of this force F resolving into the y direction with cosine theta y. All right, so that's something that's particularly useful. I can also note that this vector Fh is the magnitude of F multiplied by the sine of theta y. Right? So this is just, your typical resolution in 2D. But now if we want one more level, we want to now further resolve the vector Fh into the x and the z directions. So now let's say that we have some angle that exists here, which is this guy here. Let's call this theta x. It's the angle that exists between the x-axis and our particular vector. And we notice that this vector Fh is contained in like a two-dimensional xz plane. So it's sort of like contained in this plane here. All right. So now we can resolve Fh. Oh, let me change here. Into like components that involve theta x. Right? So it would be like, now I have here, let's do it in red. I tried to change. I ultimately want to get to resolving this into the f direction. So here's fx. And here's my fz. Ultimately, what I'm after is trying to write my force F in terms of like Fx, Fy, and Fz, right? Okay. So if this is the case, then I can write my resolved components, which is like Fx equal to the magnitude here of Fh times cosine theta x. And I could also write that my vector Fz, sorry, let's be more clear about this, but this is my magnitude of the vector Fh multiplied by sine of theta x. We have to be clear that we're using vectors here, so let's put some unit vectors on here appropriately. Okay. Now this Fh here I don't really have a unit vector associated with that particular direction. And we'll talk about that in just a second. But to fully like define the directionality of this FH, yeah, here I have the magnitude, but I also need to include some directionality. And the way that we typically do that in statics is to assign some unit vector in that general direction. And here I'm going to introduce a new unit vector that we say is just generally in like this FH direction. Let's call this lambda H. All right. So this is a unit vector in H direction. Okay, so what's like the final point? Well, the final point is if I like have one angle that I know between the vector and an axis and another angle that I know between the projection of that vector and the axis, then I can sort of figure out what all of my components are in like the x direction, the y direction, and the z direction. All right. So my point is, so if I have, let's say theta x and this theta y that I sort of showed in the picture above, and I know like the magnitude of the force, then I can resolve into components. Something like the force in x is the magnitude of this force F multiplied by sine theta y, okay, multiplied by cosine theta x. Here's the general idea. Because we know this is like my FH, magnitude of FH, okay, multiplied by cosine x, right? Continuing, I have Fy is this magnitude of F times cosine theta y. And I could continue with Fz is magnitude of F times sine theta y times sine theta x, okay? And so this would be just taking some random force that we have in space and resolving it into like x, y, z components, where here this is on I hat, this is j hat, this is k hat. Okay, so resolving a 3D force into rectangular components. Okay. Given some known angles, right? So if we go back up to this sort of picture from before, we would have to know like this theta y and this angle between this vector fh and the x-axis, etc. We would have to sort of know this information to properly resolve this. And we'd have to know the magnitude of f to resolve all of these things properly. But the basic strategies are more or less the same, is that you know an angle between the vector and an axis of interest, and you just resolve that vector into the various directions using the cosines or the sine functions appropriately, okay? So that is sort of like one way to do it. And I would say that this is like, this is one method. But this method is a little bit like difficult to work with, all right? but is very geometrically intense. Okay, you've got to like look at your picture. You've got to know what your angles are. Maybe you know those angles, maybe you don't. Maybe you have to like resolve those angles using some like geometry of the problem. It can be kind of a difficult to work with.
What's the difference between H and Z that you put?
Okay, the question here is what's the difference between H and Z? So this force H here is the projection of my original force F into the XZ plane. All right. So that force FH is the projection of this original 3D vector into the XZ plane. Then we further resolve this force FH into the Z direction using the sine of the angle theta x. All right. It would be nicer if there were some more algebraic or vector mathy way to do this. We had some sort of method for resolving 3D forces and vectors into rectangular components. So that we could just more or less write that our force is some combination of like Fx plus Fy plus Fz. That's ultimately what I would like want to do and want to sort of execute, because we're going to get to a point where we're doing like the sum of the forces in the x, the sum of the forces in the y, and the sum of the forces in z equals 0. So it would be nice if we had an easy way to just look at any particular vector in space or force in space F and quickly write it in terms of its like components in x, components in y, and components in z. It would be nice. If I had to go through like this exercise every single time and think about like, all right, what angles do I have for this geometry? Can I project it to this plane? What angle am I projecting through? And then what angle am I resolving my projection through? It's kind of like a nightmare, right? So, you know, originally taking like this guy here and projecting it into this plane and then resolving this projection into like the x direction and then the z direction. It's just like such a huge hassle. It's like this multi-step process. It's really like quite frustrating. All right. So is there an easier way to sort of resolve these forces into various directions? And the way that we can do that is using direction cosines. So let's talk about direction cosines, and we'll show you an easier way to sort of resolve forces in 3 dimensions. All right, so let's move and talk now about direction cosines. All right. So let's go back to 2D for a second so I can sort of motivate this, and we'll say that the easier method here for resolving forces into x, y, z directions uses direction cosines. Okay, and let's talk about what direction cosines are. And we'll motivate this in 2D first. First, in 2D. So remember, for your 2D situation, let's just draw an XY plane. We showed that if we had some force that's out in space, F, and we knew the angle that existed between that force F and the x direction. We typically called this theta. Then we could resolve this force F into the x and the y directions pretty easily, saying that Fx is just the magnitude of this force multiplied by cosine theta in the I hat, all right? So I hat is, again, our unit vector in the x direction. This force Fy is the magnitude of F multiplied by the sine of that angle. Okay, and this is what we saw in 2D. This is kind of like the old method. All right, and it's a good method. Nothing wrong with this. I think it's pretty easy to understand this. It's pretty easy to execute and work with this. But I want to motivate and move towards working in 3 dimensions. And to do that, it's helpful to talk about direction cosines. And so let's introduce this sort of new method where we're sort of looking at the same situation. But now we don't just have that angle theta that we work with. We still have this vector F. But we define the angle between that force F and every single axis that exists independently. So now we define angle between force F and each axis separately. And so if we do that, here we have the angle that is theta, what we previously had theta, but I'm going to specify this now as theta x. It is the angle that exists between this force and the x-axis. Right? Similarly, I could define the angle that exists between this force F and the y-axis. That is here. And we'll call this theta y. It's pretty obvious that theta y is just 90 degrees minus theta x, but just roll with me for now, all right? So now we have that Fx is this magnitude of F multiplied by cosine theta x in the I hat. And the magnitude of Fy is, the vector Fy is the magnitude of F times the sine of, times the cosine theta y j hat. And so what's the power of this? All right, well, we're writing our directionality here basically, or resolving our angles strictly through the cosine function, right? So if we know the angle that exists between the force and the axis, here that would be like theta x is the angle that exists between the x-axis and the force F. And theta y is the angle that exists between the force F and the y-axis. We can just resolve using the cosine of those angles directly without having to worry about the sine function at all. And in 2 dimensions, this seems like a stupid waste of time because, well, just use the sine function. But this trick also holds in 3 dimensions. So if you know the cosine, or if you know the angle between the force and the axis in 3 dimensions, then this idea also will still hold. Okay, so let's put that actually into words here. Okay, so given angle between force F and axis of interest, then component of force in that axis is the magnitude of that force multiplied by cosine of that angle. Right? So in 2D, obviously, we saw that the force in the x direction is just the magnitude of the F of the force F times cosine theta x I hat. And the force y is the magnitude of the force multiplied by cosine theta y in the j hat. All right. The reason why I sort of introduce this and talk about this in 2D first is because this idea holds as we move to 3 dimensions. All right. So I'll say here, not particularly useful in 2D. But very useful in 3D. Okay, so let's see what this sort of actually looks like in 3D. So in 3D, our direction cosine's basically the same idea. The component of the force in the x direction is just the magnitude of that force multiplied by the cosine of the angle between that force and the x-axis. Same thing in y. And same thing in z. This is I keep forgetting to put my unit vectors on. You guys should yell at me if I forget my unit vectors. Now we might want to sort of draw a picture of this to see what this kind of looks like in 3 dimensions. So pictorially, what this actually looks like is if we have, again, some 3D space, XYZ, and we've got some force that exists in that space. Here's F. And let's sort of like contain F as best we can, or sort of like show its projection here as best we can. Okay, let's say that that's approximately where F lies. And let's say that we know the angle between that force and all of the axes. So the angle that exists between that force and the y-axis, here we showed before, as like theta y. The angle that exists between this and the z-axis here is theta z, and the angle between this force and the x-axis is theta x. Okay. So then the individual components that make up this guy, you know, if we wanted to resolve into this sort of 3-dimensional vector, remember this is like F z, this is F y, and this guy here is F x. Then F, which is Fx plus Fy plus Fz. It's the combination or the addition of all three of these vectors together. This is the magnitude of F times cosine of the angle between the x-axis and that force in the I direction. That's like your Fx. Okay. Adding to that, the magnitude of F times the cosine theta y. So this is the angle here between the force and the y-axis. So this guy, and adding to this my z component in k hat. All right. Or obviously Fc is this guy. All right. We have a sort of a special designation for this sort of setup. And we would call these like interim values here that sort of tell us like the magnitude of sort of the total force along that particular direction. We would call these direction cosines. Okay. Where this theta x, theta y, and theta z are angles between my force and axes of interest. Okay. They're so common and so frequently used that they're often written in shorthand notation. Often written as the following. This is a script L is cosine theta x. Sort of a script M is cosine theta y. And script N is cosine theta z. Okay, so then you might see something like the following, which is my force that exists in space is the magnitude of F times the script L in I hat plus the magnitude of F times the script M in J hat plus the magnitude of F plus the script N in K hat. So that's another form that you might see a three-dimensional vector. One last thing, and then we'll do a quick example and get you out of here. The magnitude of a force in 3D, it's very similar to how we calculate the magnitude of a force in 2D, is that the magnitude of a force is the square root of the sum of the squares of the components. So it's just like what we do in 2D. This will be like the magnitude of the component in the x direction squared plus the magnitude of the component of this force in the y direction squared plus the magnitude of this force in the z direction squared. That's another little bit of information that you might have. And what comes out of this, if you sort of expand this a little bit, is kind of an interesting result. If you plug in sort of for your directional cosines, remember the magnitude of x of the force in the f direction is like the magnitude of f times your directional cosine L squared plus the magnitude of your force F times your M squared plus the magnitude of the force times N all squared. Could pull out like a magnitude of F squared out of all of this. And you're going to have something like L squared plus M squared plus N squared. All right, so that's just kind of working my algebra magic there. And continuing downwards, we can pull this guy right out of the square root. Sorry, the square would come away. And we would see this. I could square both sides. 1 squared is still going to be 1. And you get this really interesting result. Is that the directional cosines squared all added together equals 1, which is really kind of an interesting sort of phenomena. So if we wanted to spell this out a little bit more clearly, cosine squared theta x plus cosine squared theta y plus cosine squared theta z is equal to 1. This is an interesting result that sort of comes out. Another relationship in our directional cosines. That if you sort of have the angle that exists between the force and all the axis, and you take the cosine squared of all of those angles and add them together, it equals 1. Kind of crazy. All right, we'll do one sort of quick example here. This actually isn't in your notes. I sort of came up with this before class. And we'll do an example here. You have a force with magnitude 500 newtons. Forms angles with x, y, and z axes of theta x is 60 degrees, theta y is equal to 45 degrees, and theta z is equal to 120 degrees. We want to find these components fx, fy, and fz, and then express f. In terms of unit vectors. All right, so away we go. Let's see if we can maybe make a picture of this. Might help us. All right. So I form an angle with the x-axis, which is 60 degrees. Kind of have to consider all these things together. All right. So I have a magnitude of 500 newtons. X-axis 60 degrees, y-axis 45 degrees, z-axis 120 degrees. Interesting. Right. I'll sort of do my best to make this guy. I think I would end up with a vector that maybe is pointed slightly backwards into the negative z direction. Which looks like this. 500 newtons. All right. Where this angle is my theta x. It's the angle between that force and the x-axis. I'm told is 60 degrees. This angle here, this theta y is 45 degrees. And here, which is this big angle, here is theta z, 120 degrees. All right. So maybe that 500 newtons is sort of like pointing backwards a little bit. So let's use our direction cosines to sort of calculate the components in each of the three directions. And then write my force in terms of typical unit vectors in rectangular coordinates. All right. Well, pretty straightforward here. We'll just use our equations. Force in the x direction is the magnitude of the force multiplied by cosine theta x in the I hat. We plug in here. This will be 500 newtons. It's the magnitude of that force times the cosine of the angle between the x-axis and my force, which I'm given here is 60 degrees in the I hat. And we'll find my force in the x here is 250 newtons I hat. Okay. Similar ideas here. Magnitude of f times cosine theta y, j hat. This will be 500 newtons multiplied by cosine 45 in j hat. So you work this guy out, 354 newtons in j hat. Finally, my force in the z. Yeah, this will be 500 newtons times cosine 120 degrees in k hat. So here we're pointing slightly backwards, negative 250 newtons k hat. So those are like the three components of this force in the various directions. 250, 354, negative 250 in I, J, and K. Maybe we want to go back to our picture and sort of represent that on our figure. I'll give you a second to copy down if you're still working. Okay. So maybe I have like 250 in X. My Y direction, 354. Okay. And then I'm sort of pointed backwards here in Z. It'll be a little bit difficult to draw this. Maybe I'll do it in a different color. But here I'm pointed like slightly backwards in Z. Here FC, which we calculated before as negative 250, or since I'm pointing backwards here, 250 newtons kind of in the negative direction. All right. So that would be the components of that 500 Newton force. All right, so we're dipping our toe into 3D vectors, getting there, talking about direction cosines. We'll look at a couple more example problems tomorrow, a couple more complicated example problems. So that's it for today. Thanks for coming, and we'll see you tomorrow.